It is now 2:15. Thank you for joining us for the second session of the afternoon. Um, we are excited to welcome again Amy and Robert. They are here to share their project looking at improving the efficiency of watercraft inspections through more coordination and cooperation. A couple of quick announcements before I pass it over to Amy and Robert. Um, there is a Q&A function that you can use for any questions that you might have. It should be a little icon at the bottom of your screen. If you don't see it, you might need to just wiggle your mouse a little bit and it will show up. If you have any questions, you can put them there. You can type your questions at any point during the talk. We will save them all towards the end and bring them up once the presentation is complete. And all these sessions are being recorded. So if there's something that you miss, don't worry. That will get posted onto YouTube and you will get a notification once the session recordings are available. I believe that is all that I have for housekeeping and quick announcements. So with that, I will pass the baton over to, I believe, Amy first.
Yeah, great. Thank you for that introduction, Megan. And I want to thank you all for joining us today. I'm Amy Kinsley. I'm an aquatic epidemiologist in the College of Veterinary Medicine. And together with my collaborator, Robert Haight, who is a researcher for USDA Forest Service, we'll be presenting the work we've been conducting to increase the efficiency of watercraft inspection programs. And so this talk will take place into two different parts. The first, Robert or Bob will present our work identifying cost-effective locations of watercraft inspections through the state. And then the second half, I'll share our work where we're identifying ways in which counties can work together to increase inspections while saving resources. And so we look forward to your questions and comments at the end. And with that, I'll go ahead and pass it off to Bob.
Okay, the first thing I'm going to do is share my screen. There we go. Okay, Amy, is that coming in okay?
Yes.
Okay, great. Hi, everyone. I'm Bob Haight. As Amy said, I'm an economist with the USDA Forest Service Northern Research Station. My office is located on the St. Paul campus of the University of Minnesota, next door to the MASERC headquarters. I am grateful for my collaborators, including Amy and Nick Phelps, and my Canadian collaborator, Dennis Yemshanoff from the Canadian Forest Service. The title of my talk today is Optimizing the Location of Watercraft Inspection Stations in Minnesota. Aquatic invasive species like these zebra mussels shown here are a huge problem in lakes and rivers in the US. The economic impacts of zebra mussel alone are estimated to be hundreds of millions of dollars per year annually. An important way that aquatic invaders spread is on recreational boats as people move them from lake to lake. In response, state and county agencies fund activities to prevent AIS spread, including boat inspections as they enter and leave popular lakes. Our intent in the first part of this project is to develop and test a model for determining the optimal location of watercraft inspection stations at lakes throughout the state of Minnesota. The model can provide a baseline for comparing actual or proposed allocations of inspection resources. I'll begin with a background about funding for watercraft inspection in Minnesota, and then I'll provide a description of the state planner's management objective and the data that we used. Then I'll describe a baseline model for optimal statewide allocation of resources, and we'll compare the model results with an estimate of the actual 2019 allocation of inspection resources. And then based on that comparison, we'll conclude with some implications for our Minnesota planners. The Minnesota Department of Revenue disperses $10 million a year to counties for use in aquatic invasive species management and prevention programs. The funding level and the allocation formula are written in state statute. The funding allocation is based on the number of boat ramps and parking spots in the counties. And then county planners decide how to spend those funds. Across the state, about 20% of the Department of Revenue funding is used for watercraft inspections, while the remainder is used for boater education and activities for AIS detection and management. In addition to the Minnesota Department of Revenue funds, the Minnesota Department of Natural Resources funds watercraft inspection activities, including training and placing inspectors at lakes throughout the state. Finally, homeowner associations provide funds to counties to fill specific needs. Keeping in mind the multiple sources of funding for AIS management and prevention, we want to step back and ask the broad question, what are the cost-effective locations of watercraft inspection stations throughout the state? And then to address this question, I'm going to describe a model for the hypothetical situation where a state planner makes all the decisions about where to locate inspection stations to meet a particular management objective, which I'll describe in a moment. The value of this model is that its results can be viewed as a cost-effective baseline for comparison with actual or proposed decisions about watercraft inspection, which result from the hierarchical and decentralized decision-making processes that I described in the prior slide and that are used in practice. As a side note, the model that I'm going to describe here is the same as the one used for county level planning that we've discussed in previous MACERC showcases. Our county level model was recently published in the journal Biological Invasions, and it was the basis for the AIS Explorer web application, which many of you may be familiar with. Here, our model optimizes the location of inspection stations in the state of Minnesota as a whole, rather than a single county. In our state level model, the planner's objective is to identify the optimal location of watercraft inspection stations throughout the state, subject to a budget constraint. By optimal, we mean maximize the number of risky watercraft inspected statewide, where risky watercraft are ones that move from infested to uninfested lakes anywhere in the state. We have 3 invasive species in our analysis: zebra mussel, starry stonewort, and Eurasian water milfoil. We used 3 kinds of data. First, we have a list of counties and lakes within those counties. There's 87 counties and over 9,000 lakes. Next, we have a list of infested lakes. There are 471 lakes infested with one or more of the 3 aquatic invaders I listed before. Finally, we used estimates of annual boat movements among the lakes. These estimates were based on boater interviews between 2014 and 2017. Each boater was interviewed as they entered or left a lake and identified where they had been and where they were going. Then our colleague Zoe Cow used those boater responses to estimate the annual number of boat movements between each pair of lakes statewide. Using these estimates, we created a 9,000 by 9,000 element matrix of annual boat movements from each source lake to each destination lake. By tagging lakes according to their infestation status, we identified each link between an infested and an uninfested lake. And we identified the estimated number of risky boat movements for each link. Overall, we found an estimated 733,000 risky boat movements in the boat movement matrix. Then we use those data in the model for optimal statewide allocation. Again, the state planner's objective is to select lakes statewide for inspection stations to maximize the number of risky boats inspected. The constraints include a counter for the number of invaders that could possibly move between each pair of lakes. And it includes a binary variable for whether risky boats are inspected when they move between each pair of lakes. Finally, there's an upper bound on the number of lakes that can be selected for inspection. Our analysis involves solving the model for optimal statewide allocation under alternative levels of the budget. And here are the results. The number of risky boats inspected increases with diminishing returns. This graph shows on the vertical axis the number of risky boats inspected as a function of the number of lakes selected, the upper bound on the number of lakes selected, which is on the x-axis. And the optimal solution increases with diminishing returns as the upper bound on number of lakes selected increases. Almost all risky boats are inspected by selecting 400 lakes, which accounts for 725,000 risky boats being inspected. This result makes sense because there's 471 infested lakes, and all risky boats could be inspected if those 471 lakes each was selected for an inspection station. To put these results in perspective, we compare them with the performance of an estimate of the actual set of inspection stations that were deployed in Minnesota in 2019. In this estimate, inspectors were deployed at 409 lakes, represented by this green mark here. According to our boat movement data, an estimated 450,000 boats, risky boats, were inspected using this estimated deployment here, which is 40% less than the number of risky boats inspected using the optimal set of 400 lakes here. To show how the selected lakes are distributed among counties in the optimal statewide allocation, this map is color-coded according to the number of selected lakes for the 400 lake solution, where the darker colors represent more lakes selected. Overall, lakes are selected in 48 counties, and the top 6 counties here include 183 selected lakes, almost half the total budget. These counties are located in the Twin Cities metro here and in central Minnesota in the Lakes counties. These are the counties with the most lakes and the most risky boat traffic. This slide shows how the selected lakes for optimal statewide allocation compare with the estimate of the actual 2019 allocation. Compared to the optimal statewide allocation, the estimated 2019 allocation covers 34 counties and focuses on lakes in north central Minnesota, with fewer lakes selected in counties in the Twin Cities metro and south down here. The 6 counties with the most lakes selected in the optimal statewide allocation here have far fewer lakes selected in the actual 2019 allocation here. Now, there's several caveats associated with our estimate of the actual allocation of inspection resources. Our estimate is based on county reports of inspection station locations and hours in 2019. We selected lakes that had more than 40 hours of inspections throughout the 2019 season and left out about 150 lakes that had fewer than 40 hours of inspection. Also, the data was missing for several important counties, including Aiken, Otter Tail, and St. Louis counties, which are marked in the crosshatches here. And the data did not include DNR inspection stations, which 176 access points in 2019. In conclusion, our main research question was, what are the cost-effective locations of watercraft inspection stations throughout the state of Minnesota? To address this, we created a model for the hypothetical situation where a single state planner makes all the decisions about where to locate inspection stations to maximize the number of risky boats inspected. We know that this is a hypothetical situation and that the solution and that's not how things actually work. Nevertheless, the model can be used as a baseline for comparison of actual or proposed allocations. Our results show that statewide, almost all risky boats can be inspected by putting inspection stations at 400 lakes. Most of these lakes are already infested with one or more invaders and have large amounts of outgoing boat traffic to uninfested lakes. Our estimate of the actual 2019 selection of 400 lakes is not efficient and accounts for only 40% fewer risky boats inspected compared with the optimal statewide selection of 400 lakes. It is important to note that our estimate of the actual selection of 400 lakes is based on incomplete data, and we're working with our partners at the Minnesota DNR to improve our estimates. Notwithstanding the limits of the data, our statewide model is useful by providing a baseline to evaluate the efficiency of actual statewide inspection locations or proposed allocations. Now I'd like to pass the baton to Amy, who's going to discuss ways to think about cooperation among counties to improve the efficiency of inspection. And I'll stop sharing. There we go. And Amy, over to you.
Great, thanks, Bob. Let me get set up here quickly.
Yep, that's coming in.
Okay.
Perfect.
Great. So in the second half of the talk, I'll present the work that we've been conducting this past year, where we're focusing on ways in which counties can collaborate to increase the efficiency of their watercraft inspections. And so this is ongoing research, and I'm sharing some preliminary methods and results with you that we've been working on with our collaborator, Nick Phelps. And so the concept of collaboration amongst counties is not new. In fact, the benefits from collaboration was one of the main themes of the DNR's 2019 county workshops, where counties reported receiving additional support from local organizations such as townships and lake associations. In addition, counties reported working with park districts, watershed districts, and lake associations, as well as their neighboring counties on inspection and educational efforts. And they reported that they saved time on travel and redundant administrative duties by doing so. And so given the considerable effort that counties invest in preventing spread through inspections and the current interest in collaborative initiatives, we really wanted to answer two key questions. The first was, how can counties work together to increase the number of risky boats inspected while saving resources? And the second was, how can counties fairly share costs when working in a collaborative group? And so to answer our key question, the first key question, we turned to the Boater Network data set that Bob described in his presentation. And so that data set estimated the annual number of boats that move between lakes in Minnesota. And it also statistically accounted for movements at lakes that were not inspected and biased due to unequal inspection effort at locations where inspections did occur. And from this, we went through and identified all water bodies that either sent or received risky boats. Again, where risky boats are those that move from infested to uninfested water bodies defined by the Minnesota DNR infested waters list. And we focused on those that moved outside of the county. And we considered zebra mussels, starry stonewort, Eurasian water milfoil, and spiny water flea as species of interest in this analysis. And then we identified and we ranked counties that sent the most risky votes to each county in the state. And we looked for mutually beneficial pairings that we call reciprocal relationships. So for example, let's consider County A and County B and their top 3 sources of risky votes. In County A, we can see that the top 3 sources are County B, C, and D. And for County B, the top 3 sources are A, C, and J. And if we consider only the top senders, we can see that there is a reciprocal relationship between County A and B, which could be an opportunity for collaboration. And we can visualize this relationship as a network where the counties are nodes depicted as circles and the lines connecting them as edges that represent mutual out-of-county risky vote movements. And so to reiterate this point and then add a bit more complexity, let's consider adding 2 more counties, C and D, and their top 3 rankings. We can see that this reciprocal relationship still exists between A and B. And we can also see that a reciprocal relationship forms between County D and B, and also D and C. And I'll give you a moment to think about what that network might look like. If you want to jot it down, if you have some paper handy, or you can just create in your mind what you think that network might look like based on what we described in the previous slide. So you may have come up with something like this, where you see A and B connected like before, but now we have added D to B and C to D. And so visualizing the network as a graph like this can help us see not only who's connected, but how they're connected as a whole. And so I progressively repeated this, considering all the top senders for each county in the state. And what I found was that for the top rankings, 4 groups were formed that were made up of Carver and Hennepin, Ramsey and Washington, Cass and Crow Wing, and St. Louis and Lake, and that the average group size was 2, which makes sense because if we're only considering the top 1 connections, we're only going to have pairings of 2 arise. And as the number of ranked connections increased, so did the average group size, and the number of groups, though, ended up decreasing. And we can see that at the extreme level for the 6th ranking, we ended up with 1 large collaboration of 20 counties, which is clearly not a functional collaborative group. It's likely much too large. But that gives rise to the question, what is the ideal group size for collaboration? And so to answer that question, I turned to sociological studies, who suggested that the ideal group size ranged somewhere between 4 and 8. And that the most widely accepted ideal group size is 5, and that as the group size increases above that number of 5, there's a loss in productivity and cohesion. And so moving forward with in the analysis, I selected the 4 groups considering the top 3 connections that had an average group size of 4.5. And so here I'm showing those collaboration networks on the right. We have collaboration A, which consists of 6 counties, including Aiken, Mille Lacs, Crow Wing, Cass, Beltrami, and Itasca. County B has 4, including Pope, Ottertail, Douglas, and Todd. Collaboration C is made up of St. Louis and Lake counties, and collaboration D has 6 counties, which include Carver, Wright, Hennepin, Anoka, Ramsey, and Washington. And an interesting thing to note is that networks take on shapes based on their reciprocal relationships that might highlight the importance of certain counties. So for example, we have collaboration A and D, which are both made up of 6 counties, but they take on entirely different shapes due to the number of reciprocal relationships each county in the collaboration forms. So for example, in collaboration A, we see that Crow Wing and Cass both have 3 reciprocal relationships formed within this collaboration, and that the remainder of the counties only have 1. Where in collaboration D, we can see that Hennepin has 3 of these reciprocal relationships, where Carver, Wright, Anoka, and Ramsey have 2, and Washington's the only one that has 1. And you can imagine how those with more reciprocal relationships may benefit more from the collaboration, or they might be playing a key role in the success of the collaborative network. And so to answer our second question, we wanted to know how can counties fairly share costs when working within their collaborative group? And so to answer this question, we turn to the method called the Shapley value, which is a solution and concept in game theory that involves distributing costs or gains to actors that are working in a coalition. And what it does is it estimates the expected marginal contribution of a county after all the possible combinations of counties have been considered. And so we use this following equation where we considered the number of counties, the coalition of counties, and that takes into account all the potential configurations of those counties within the collaboration network. And then we also considered a payoff of the coalition, which I used as the number of risky votes inspected. And I made the assumption that we were able to inspect all of the risky votes. And so the Shapley values are, as I mentioned, rooted in game theory, which is the study of mathematical models of strategic interactions among decision makers. And it falls under this umbrella of cooperative games, which predict which coalitions will form and how payoffs can be split or how costs can be shared. And so just some real world examples that I have listed here are that these Shapley values have been used in marketing to determine which marketing channels attract the most customers and how to invest in those channels in the future. It's also been used to decide which menu items get added in a restaurant, considering that different items might be sharing similar ingredients. And it's also been used for collaboration between transportation organizations where they share the same supply chain. And so here I'm showing the results of these calculations as pie charts. And I purposely excluded any specific values on there because these are preliminary results. And I just wanted to highlight this in concept. But what this shows is how costs could be shared amongst counties in the collaboration, which can also be thought of as the relative benefit of participating in the collaboration. And we can see that the largest potential benefit would belong to Crow Wing County in collaboration A, and Douglas in B, Hennepin in D, and it would be split evenly between St. Louis and Lake in C. And so in the future, we want to break this down and analyze what's happening within these counties at the lake level. And so here I'm showing the top 3 connections among lakes in the collaboration, where the collaboration corresponds to the different panels in the figure. And even just looking at those top 3% of connections, we can see that there's a subset of the network that's more highly connected that could be used to identify sentinel lakes for inspection locations or even surveillance networks. So I'm going to point out some of those highly connected subgroups within the network that seem to be arising from my point of view. And that's just visually inspecting. We can also use metrics to quantify how large those groups are. And then within those groups, which lakes are actually playing a more important role based on those primary, maybe even secondary connections. So in the future, we also want to answer the question, can highly functioning collaborations get us closer to the results of the optimal state model that Bob presented? And we also want to share useful outputs of this work through AIS Explorer, which is our interactive online dashboard that Bob mentioned. So in summary, when developing collaborative networks of counties that are based on reciprocal relationships of risky boat movements and increasing those number of rankings considered in the analysis, the average group size increased while the number of groups decreased. The top 3 rankings provided 4 groups with an average group size of 4.5, which based on the sociological literature suggested that that was considered the more effective group size. And so further social network analyses at the lake level may help us understand where and how county collaborations can best help us focus our efforts. And also those Shapley values provided results that seemed promising and working towards a solution on how to fairly share costs among members in the collaborative group. So with that, I would like to send out a special thanks to Tina Fitzgerald and Adam Dahl for their input and insight. And with that, I'll take any questions you have, and then also mention that here we're throwing out some questions to you guys as well, because we're really interested in hearing your feedback. And so there's just a couple of prompts to think through while you're formulating your questions. And if you have any questions later beyond the showcase that you want to reach out and ask Bob or I, our emails are listed below. And so I'll leave that up for just a moment.
Great, thanks so much, Amy and Bob. There are a couple of questions that have already come in through the Q&A, so I will start working through those. For those who are listening in, feel free to continue to add questions in to that Q&A section as they come to mind. The first question came up during the first part of the presentations, and the question was, why is the DNR data not being considered for the statewide allocation?
Right. Yeah, that was an oversight on my part. I think this is a work in progress, and I'm still getting my hands around all of the inspection activities that are going on in the state. And so I'll include the DNR data allocation, inspection allocation data in the next round. Thanks.
Great, thank you. The next ones I think have a couple of different questions about the way the model considers certain activities and lakes. So the first one says in the statewide allocation model, it says that most of the 471 infested lakes would be allocated inspectors. So if exiting boats are not required to decontaminate or have a 5-day dry time before going to another water body, what stops the spread to a non-infested lake? And so how does focusing on infested water bodies help prevent the spread of AIS?
Right. So the questioner is correct. We're assuming that all boats that exit an infested lake, I mean, if they're inspected, then that inspection is successful in preventing the movement. And so if I was to work on improving the model, I would try to estimate the efficacy of the inspection process, as the questioner suggests, and try to account for that in the model as well.
Great, thank you. Along somewhat similar lines, the next question I had wondered about, if you're not looking at movements from infested lakes to other infested lakes, are you potentially missing the introduction of a different invasive species into a lake that's infested with one that's not a match? So for example, a spiny water flea being introduced into a zebra mussel infested lake.
I'm not exactly sure what they're asking, but let me just think about this for a second. Well, we do look at we do look at the movement from infested lakes to infested lakes, and we count risky boat movements if an infested lake, if say zebra mussel is in one of those infested lakes, but not in the other infested lake, which may be infested with spiny or with Eurasian water milfoil. So we do, that was the counter that I mentioned in the model, which counts the number of species, AIS, that could potentially be moved from one lake to another. And both of those lakes could be infested with one or more species. I don't know if that gets at the answer or not, but maybe they can follow up.
Yeah, and I just wanted to elaborate on that because I think that question could also pertain to the modeling that I was doing as well. And mine functions similarly to the way Bob was describing, where if there was at least one of those, if there was even at least one of those invasive species in the lake, we considered it infested, but we also considered that if it was already infested with zebra mussels and starry stonewort and was going zebra mussels to a starry stonewort, that we accounted for that. And that there could be already infestations that were not part of the species of interest that we were missing. And so that's something that I think would still show up as an infested to uninfested movement. And again, if that's not clear, we can elaborate further with this person.
Great, thank you. The next question is looking more specifically up in the Boundary Waters area. So noting the large number of lakes in the Boundary Waters and Quetico region, and saying that these lakes don't have boat ramps or parking spots, but are still vulnerable to the introduction of AIS through motor access lakes and destination lakes from outside the Boundary Waters. The current model doesn't seem to accommodate those. So are there ways to modify the model to help protect that boundary water region?
Right. Good question. So I want to make clear that the model that we developed is allocates resources to maximize the number of risky boats inspected. And a risky boat is one that moves from an infested lake to an uninfested lake. So we do take into account the movement of risky boats into uninfested lakes in the boundary waters, in the counties, in the lakes that are in the boundary waters. I think when the questioner was saying that we don't account, that the number of boat ramps and stuff, that comes into play in the State Department of Revenue allocation formula, not in our model. So I just want to make that point clear.
Great, thank you, Bob. The next question was looking at the data for the number of risky boat decontaminations at the DNR boat landings, and this person has noticed a decline in recent years. Do you happen to know how widespread that decline is, and if we know why that's occurring?
Okay, just a second. I'm reading this question.
Sure.
So what Hans is saying is that the number of boats that are decontaminated at DNR boat landings has declined in recent years. I'm not the best. I don't have information about that. So that's something that our DNR colleagues would be better off addressing, like Tina or Adam.
That sounds great. I can find and drop in a chat later a link to contact DNR if you have some specific questions like that aren't able to get answered here as well. The next question was wondering about if the risky lakes are determined using the data from the AIS Explorer.
Right. Amy, you want to take that?
Yeah, so it is. So we're using the same data that AIS Explorer is running. I think the only difference that might show up from what AIS Explorer is running to maybe the analysis that Bob is running is that AIS Explorer automatically assigns lakes that lie on boundaries of counties. So if one lake sits within 2 counties, it ends up showing up on the analysis for both. And I believe in Bob's that that might be allocated to just one of the counties. Is that right, Bob?
Yes.
And so that's the only difference. But yeah, the risky lakes and the way we determine it based on the species of interest would be similar for my analysis. I believe that AIS Explorer also accounts for spiny water flea, which Bob's analysis didn't, but otherwise, yes, they'd be estimated in the same way. Mm-hmm.
Wonderful. Okay, moving on to the next question. This one says, Bob, when a county wants to use your optimization work to determine where to send their inspectors, should they use the state optimization information and filter for the county, or should a separate county model be done?
I recommend working within the county I recommend working with your county lakes and developing a model for those lakes alone. The model that I described today is really for a hypothetical situation where there's a single state planner who makes all the decisions. And I don't think that in that situation, a state planner may not have the best interests of each county planner in mind in that hypothetical situation. So you're better off just working within your own county, like we've done before for Stearns and Crow Wing. Yeah.
Great, thank you.
Yeah, plus one more thing about that is that we've been, a key component of our modeling is the estimates of boater movement between pairs of lakes. And I found, and probably Amy, you've found too, that when we consult with individual counties, they have additional information that we can use to augment our models. Information about the rate of boats entering and leaving particular launch sites and so forth. And through consultation, we can use that additional information to help improve our models.
Mm-hmm.
Great. All right. It looks like we have 2 questions left, which I think should be about perfect for the amount of time left. The first one of those is wondering if you've looked at how boater movement changes from year to year. So for example, from 2014 to 27. And from that, is it appropriate to compare models developed then to say 2019?
Yeah, so that's a great question. And that's actually one we're attempting to answer in the near future. So one of our goals for follow-up in this project and other projects we have funded is to answer just that question, right? We want to know, how is that boater movement changing from year to year or within these kind of groupings of years? And is that going to influence our model outputs? And so if it does, in what ways? And so we're hoping that that's something we can share with you maybe by the next showcase, actually. So it's a great question.
Great. Way to set the stage for next year too. That's wonderful. All right. And for the final question of this session, the question is, does the model account for private accesses or resorts that may not have inspectors at their access?
Amy, do you want to take that one?
Yeah, so I think when I mentioned the boater network data that we were using, I described it as, it's estimating these movements between lakes in the state. There's over 9,000 lakes that it estimates the movements between, and those were from inspections that were observed. But then it also estimates movement to those that were unobserved. So even if there's private accesses and resorts that didn't have inspectors at their accesses, my understanding is there are predictions of those movements for those locations. But if we don't have those locations as potential places to have inspectors, I don't believe they're considered in our analysis. Is that correct, Bob?
Yeah, I think it's important just to say distinguish between the unit of analysis that in our boat movement matrix and what the questioner was asking about.
Mm.
We're estimating the movement from lake to lake, not from boat launch to boat launch. Mm-hmm. So if our estimates are based on, like you said, Amy, we use statistical analysis to adjust for lakes that didn't have any boater survey information for them, and we really don't pay attention to or account for boat launches, whether they're public or private.
Great point.
All right. Thanks for those great questions. That was terrific.
Great. Thank you so much to everyone for joining us today. Thank you, Amy and Robert, for sharing all of this information.
I see Bruce here from Beltrami County is asking that this could get added to AIS Explorer. How will that change the results of the tool? I use AIS Explorer to look at in-county traffic. Should I include other counties when I use that tool? And I think that's a great question. So right now within the watercraft inspection tab, you can't really include other counties within that analysis. You can go to the risk for surveillance model and kind of take a look at the networks and see who might be moving boats within your county. But right now, the watercraft inspection tab considers those out of county movements into the county. So if you're just considering your county, you should be kind of taking that into account into the analysis. When I say that we're going to incorporate that into AIS Explorer moving forward, I'm really thinking of ways in which we can foster collaboration. So ways in which we can share the types of networks that I was showing today to say who would be my ideal partner based on what we know about voter movements. So, and that's still open for what that would look like and how that would function. So Bruce, if you're there and you can hear me, if you have any specific ideas or you want to be part of that conversation, I can put you down as a person on my list to reach out to, and we can kind of include you in the brainstorming sessions as we move along. So thanks for that point.
I have a question for you.
Sure.
My question is, when you use the Shapley values, are they used to determine how resources should be shared among counties in a group? Something like that?
It could be resources or it could be costs. So it's just based on that like marginal contribution. So here I consider that marginal contribution to be risky boats that county is contributing into the collaboration. So you can imagine that that would mean that those that have more risky boats moving amongst those within the collaboration would need more resources to manage it potentially, or they're playing a more critical role when you consider voter movements that are occurring within the whole network, right?
I see.
So I kind of see those as one and the same,
Mhm.
but I have had that question come up before.